All right, so you can probably tell from the lecture title that we're going to start talking about processes and threads, and this is probably the easiest lecture we'll have on this topic. It's going to get very sophisticated very quickly, so we'll just dive in. It shouldn't be too scary. I think that all of it you guys can handle, but like I said, it's going to get very quickly to the point where you have to sit down and think very carefully about how your OS works to make sure that everything works properly. So I saw a little bit of discussion on the Piazza about interrupting other interrupts, and it's that kind of thing that we'll start getting into in a couple of lectures where it's like, okay, I need to understand conceptually what the constraints are in my system so that you can make sure it works correctly. Okay, so we have processes, which is of course short for a sequential process because typically the process is a single logical control flow. We're talking about single-threaded processes because we haven't introduced the notion of threads yet. But anyway, this is the primary way that multitasking is actually offered in these operating systems. So we have the program text, what should be done. We have the CPU state, where are we in the execution of those instructions. We have the current memory state because that's obviously part of the execution state, and various other resources we need to keep track of. Open files, open sockets, blah, blah, blah. So Tannenbaum's OS book actually has a pretty good analogy, which is that the CPU is like a chef, and the program is like a recipe, and all of the various bowls or the stuff that's in the oven and so forth is like the process. So you have the recipe is being executed by the chef, and the chef, a good chef is really good at multitasking actually and can do multiple things concurrently, keep multiple processes or multiple recipes cooking at the same time. The CPU is very similar in how it does this. Okay, so the OS is responsible for managing this, and of course, even with a single processor or a single CPU, we can still execute multiple processes concurrently because it turns out that most processes do some I/O, and then some computing, and then some I/O, and then some computing. They have what we call CPU bursts and then I/O bursts. And so if you have processes behaving in this typical way, then you can overlap their logical flows and present the illusion of, well, it's not really an illusion. You're saying that they execute concurrently. It's really more of an illusion that they are executing in parallel, but we'll talk about that next lecture. Okay, so you can represent this as a state diagram, which we have talked about a lot in CS24, so we'll just go over this now because it's a lot more relevant. You have to create processes, and they have a number of places they can originate from. Obviously, when you call fork, which you all had to do in the first project, then you can create a new process that's a clone of yourself. There's another process which is really interesting. It's the very first process that's actually started by the operating system. I say init, but that's not actually what we use very much anymore. Does anybody know what we use now? I don't know if you've heard of systemd. Yeah, do I actually say this here? No, I don't. So, yeah, systemd is the new thing. It's causing a lot of consternation among sysadmins. I personally don't like systemd because it's much more complex, but whatever. They're trying to solve a real problem, and it's just that people don't like change. Anyway, so you have various ways to start processes. And so of the processes that are on the system, some of them are able to use a CPU if they had it. So they're not waiting for some I/O operation that might take a million clocks. They're not waiting for that to complete, so they could actually make progress. But of course, for each CPU, we can only really execute one process at a time. So we have a running state where it's actually on a CPU, and we have a ready state where it could run, but it doesn't have a CPU to run on. So CPUs are limited resources. We typically have many more processes than CPUs. And so we have ready processes which would like a CPU. They could make use of it, but you only have as many processes in a running state as you have CPUs. Okay, now, of course, you don't get the CPU right away, so processes will go into the ready state initially. And it's a collection. We typically call it a ready queue. But that's actually a really bad misnomer because the data structures we use to represent the set of ready processes can be very sophisticated. When we start talking about scheduling and we look at how Linux schedules processes, you'll see that it's got a number of very sophisticated data structures that it uses for managing these ready processes. Okay, now of course the CPU is only allowed to be held for a certain amount of time, so when a timer interrupt goes off, then the OS gets invoked and it will boot that process off the processor, so the time slice expires. And of course it can execute the scheduler to pick another process to get the CPU, so that's how we transition from ready to running. Okay, now when we have long-running tasks, we need to wait. And so in that condition, processes should not receive the CPU because there's no way they could progress anyway. So we move them into a special state called blocked. And they stay there until basically some interrupt triggers to say, hey, now you can move into the ready state again. So instead of holding everybody up, we move the process from running to blocked. Okay, so interrupt goes off. You guys have all experienced that now, how wonderfully exciting it is to see interrupts go off. I tell you, when I ran through my house saying, I got hello to print on my screen, it was magical. Same thing, like keys, I can press keys and stuff happens, and it's just same thing. So interrupt goes off. We can typically move some process or processes into the ready state from the blocked state. And of course, they eventually terminate. They could live for a long time, or they might live for a very short time. It sort of depends on, the purpose of the process and also how well it was written, I suppose. But anyway, there's various things that need to happen when a process terminates. So we need to be able to do our add-exit processing. You may remember that from CS24, that if you exit by returning from main or by calling exit, then there's various exit handlers. You can register exit handlers to run, which is actually really nice if you want your program to shut down cleanly. And so those things are run. If you terminate in a few other ways, then you don't get to run add exit handlers. So you sort of probably shouldn't count on being able to do that, but you could. And of course, processes stay in this terminated state until they get reaped, at least on Unix, so that the reasons for termination can be understood by somebody else. So like I say here, various reasons, voluntary termination by the process itself. So it returns from main, it calls exit, something like that. And typically the way that the entry point works for Unix is it'll just be like exit main. So whatever main does goes into exit, and that's the status code that's returned back to the operating system kernel. So that it's a very straightforward way of doing things. Okay, involuntary termination due to an unrecoverable fault in the process. You generate a seg fault, or you have some other issue that occurs and you get a signal that kills you. Or involuntary termination due to a signal from another process. So I control C a process and it sends a sigint, and the default sigint handler is kill the program. Or sig term, which again the default behavior is to kill the program, but you can handle it and ignore it if you would like. Sig kill thankfully cannot be ignored. That's the number for that is 9. So if you ever do a kill minus 9 to a program, which you have to do from time to time, it sends a sig kill to the program. Okay, so that is usually sufficient as far as we need, but Unix beefs this up a little tiny bit by introducing a couple of other states, which again you've probably seen before. If you've ever hit Control Z, anybody done that? You don't terminate the process, right? You put it into the background, or really what you're doing is you're suspending it, and then you can put it into the background if you'd like. But anyway, that sends a sig stop or a sig t stop to the process, which moves it into this ready suspended state. Okay? Now it may be ready, or it may actually be blocked on some I/O, and so in that case we also need a blocked suspended state to keep track of the distinction there. Okay? So I happen to hit Control Z, and the program happened to be in the middle of an I/O that's still going to be running for a few 100,000 clocks more. Then it's going to be in blocked. So then it moves to block suspended, and when that interrupt triggers saying, hey, your data showed up, then it can go ahead and move over to ready suspended. Okay, so this is the final process lifecycle, at least as far as Unix is concerned. Okay? I imagine there's probably a way to take a Windows program and put it into the background, but I don't know it offhand. So it probably has something analogous, but I don't know what it is. Is there anybody here who really loves programming on Windows, like Windows system programming? I hear snickers, I understand. But I mean, there's always a couple, and they don't like to admit it, but it's you know, it's great if you want to do graphics programming. DirectX is really cool. Okay, so how are processes resources managed and reclaimed? How are block processes managed by the OS? How do we switch what process is currently running? So we're going to talk about this probably in more detail than we ever have, but it's still not going to be nearly enough detail to understand what goes on in the OS. So we're going to revisit that question when we start developing the implementation details of how this whole model works. And of course, how does the OS choose what process should run next? So that's really the question of process scheduling. Okay? So these are important questions that we need to understand, and we're going to start going through these basically in sequence as we go ahead and unravel how this all works. Okay, so we have some data structure that represents all of the details of a process. Like I said, the program text is part of this, and also the execution state. So we have things like registers, open files, memory, virtual memory configuration, so forth. Okay, and typically, at least historically, it was called a process control block. In Linux, it's actually called a task struct, and Linux doesn't make a lot of distinction between processes and threads. In fact, threads are kind of what Linux manages and schedules on, which makes it very easy for Linux to support multi-threaded programs. So task struct tends to be how Linux refers to these things. But this is a very simple representative example from older OSs, which I kind of continue to use because it does capture all of the relevant details. So we have identification, state information, status information. So that was, you know, am I able to run if I got a CPU? Am I blocked on some device? If so, what device? And so forth. And hierarchy information and other information. And when you look in Pintos, because Pintos has this thing called a kernel thread, which we'll talk about more starting next time, then it has various details like this in the thread object. So we have what queue are we in? Are we in the ready queue? Are we blocked on something? And so forth. And then we have some, I can't remember if it actually has hierarchy information or not, but you have all of these same kinds of details in Pintos's representation of processes. Okay, so process identification. We need some kind of process ID. We need to map it to the data structure for the process. Very simple to do. We just need some simple data structure that can map that int to a pointer. That's rocket science. You might think, well, a really easy way to do this is to have an array, and the process ID is just an index into that array, and then the entry in the array is a pointer to the process control block. Well, that would certainly be an option, except you're expecting that you're always going to have most of your processes, you know, available processes to run are actually in a running state, which is kind of a bad assumption if you want a responsive computer. So they tend to use a sparse representation instead. Hash tables are great because it turns out that you can hash ints really easily, and pointers are easy to pack into buckets, so why don't we just use some kind of hash table representation? Okay. Now it kind of introduces a new question, which is if you've got this hash table and it's living in the kernel and the kernel has a limited amount of memory, then how do we actually do kernel memory management? That's something that we're going to talk about in the future. But you might remember how we talk about memory fragmentation issues in CS24. And remember that fragmentation is an issue the longer that a program runs, and especially if the program allocates blocks of varying sizes and then releases them. They have various life cycles, and they're allocated and released. Well, there's one program that runs longer than any other program on your computer. It's your kernel. And your kernel frequently has a lot of different size things that it has to allocate. So how we manage memory in these systems is important, and it also has a lot of subtleties. So we're going to revisit that issue in a probably a week or two and talk about how kernels actually manage memory, because it actually affects how these APIs are exposed, and it affects how kernels frequently work with user programs. So we'll revisit that in the future. Okay, now we also have process hierarchy, where you can see we have a parent process and a list of children. Every process has to have a parent. Now, this is a Unix constraint. This is not a Windows constraint. Windows has a very much looser way of doing this. But every process has a parent, except I suppose init. Init doesn't have a parent because, you know, it's the very first process, or the equivalent in System D. And if a parent process terminates before its children do, then the children become children of init, or the whatever the ancestor process is. Anybody remember what it is for Macs? The equivalent of init on the Mac? I can't remember off the top of my head. It's launchd. That's what it is. Launchd is the parent of every process on the Mac. So you can see that different operating systems have different solutions for this. It's not always just necessarily init. Okay, so yeah, not every operating system provides a hierarchy. Windows is a notable example that doesn't really impose a hierarchy. You can group processes and you can have leaders of groups and so forth, but they all are kind of peers on Windows. Okay, state vector, so this is all the context information. So you have CPU state. What process capabilities do you have? I was working on an interesting project, and if you want to set resource limits on processes, your process has to have certain privileges to do so that are obviously associated with being the root user or some user in a particular group or things like that. So you have capabilities, protection information. When it's suspended, you have register state, you have program counter, you have other details like that, flags, and let's see, CPU number when you're running. So this is interesting. If you have multiple cores, it's nice to know which processor you're running on, because maybe when you resume that process, you'd like to resume it on the same processor, just in case there's still memory in the cache, that process will now not have to load from main memory. So there's things like that. Also, sometimes you've probably heard of specifying processor affinities. So you can actually say, I would like to always be on this one processor when I run. And again, typically that's done to maximize cache utilization of programs. Memory, so contents of the process code, data, stack segments, and so forth. And then various other resources. Network sockets, files, pipes, Unix sockets, all of those kinds of things you might have listed in your resources. The things that the process has open. Because guess what? When the program terminates, all those resources need to be cleaned up by the operating system. You know, you remember the whole thing of process A opens a file, process B deletes the same file, now there's no more directory entries to the file, process A terminates, now the OS needs to go in and actually clean up the file that process A had opened. So those kinds of things need to happen, so that's why we have collection of resources. Now there's also scheduling details, so we have these kinds of states, which we already talked about, basically saying, what is the current status of the program? Can it actually run if I gave it a CPU? Is it blocked on some device? And of course, there's various other details as well that we might want to record, like what's its behavior, so that we can do scheduling and so forth. Okay, so those are basically, let me go back here real quick. So those are basically all the general details that we capture for every process. We can add other details. We'll actually start developing this model a little bit more to make some of our operations pretty easy. But are there any questions about the process information that goes along each process? Okay. This is like pretty easy so far. So we haven't gotten into anything really, insanely complicated. Okay, so process A is executing along, and then something happens. Maybe the disk controller fires an interrupt to say that some sectors got loaded into a disk buffer that the OS set up. Or a timer goes off to say process A should no longer have the processor. Or let's say process A decides to open a file or something like that, and we know that it's going to take some time before that thing can actually be opened. Okay? So when that event occurs, we switch into the kernel. And we've only talked very briefly about this. We understand that there's kernel space and user space, and we have some protection capabilities. We understand that the code is probably running in this user mode thing we've talked about, and now we need to switch into kernel mode. But remember that all of this goes through an interrupt handler. So you all have written interrupt handlers now. If you haven't, then you're way behind on the second project. But what's one of the very first things you do in the interrupt handler? Anybody remember? Yeah, you do like a push A, right? And that pushes all the registers onto the stack. And then you can, I can't remember, does that push the flags register, or do you then have to do a push F? I can't remember.
Interrupt. It
You're right, because the interrupt flag is cleared, and then, so, yeah, the original flags is saved before, as part of the interrupt dispatch process. Okay, so you have all this stuff that's pushed onto the stack. Well, guess what? If I hand somebody a pointer to that data on the stack, that can be the program's context. At least now I have the register state saved. I can save a few other things if I'd like, and that actually can be exposed. There's some Unix APIs for signal handling that expose that information. It's crazy. Because if you manipulate that, then on the trip out of the interrupt handler, all of that gets restored, and if you made any changes, the changes get applied to the registers as well. But so we have some basically details of the process's execution context that gets saved when we do the trap. Okay, so this is the kind of thing that's going on. CPU state, registers, program counter, stack pointer, status flags, all of these things are saved by the interrupt dispatch process. And then various other things are already saved into the process control block. There's another good reason why we have to do that, because the kernel needs to run code, and the kernel doesn't want to have to worry about blowing away the process's details. So all of that information needs to be saved so that the kernel can then do its thing. Okay, so we have a little bit of time spent on saving CPU state. We do kernel task stuff. Then we have to, let's say that we switch processes. Okay, and so in this case, let's say that it's something other than get PID or get ppid, which are very simple operations to perform. So they're opening a file, the timer interrupt went off, and they have to get kicked off the CPU, something like that. So the kernel ran the scheduler, it said, okay, now it's process B's turn. And so it switches to something else and then exits out of the interrupt handler, and that restores the CPU state of process B. And then process B gets to execute. Okay? So this is a rough guide as to what's going on. And you can think of like what is going on in each of these details. You'll see it much more when we get into the implementation of this stuff. The important detail here is that this definitely takes time. And while we're spending time doing this stuff, we're not spending time running actual real program code that we care about. Okay? So, like I say here, the entering into the kernel, we probably will have to switch stacks. So you use your task segment configuration, all of that kind of stuff. Yeah, and like I have here, you save the program counter, you save the flags. Probably the very first thing on your interrupt handler is you're going to save all the registers so that you can do whatever you want in your interrupt handler, blah, blah, blah. Okay, then the kernel has to run the scheduler. You want the scheduler, remember, it needs to be fast and it needs to make good choices. Good luck with that. So that's an interesting challenge. Most system calls will cause a context switch, so most system calls will invoke the scheduler. Okay. Then on leaving the kernel, you have to restore the CPU state, and we kind of made that sound easy. Okay, we have a push A, and then we just pop A, and that restores the CPU state. Well, it's a little bit more than that, because we also have the virtual memory configuration, and we have to load the virtual memory configuration. So that's another thing that has to happen. So control register CR3. I don't think you specifically have to mess with this. Thankfully, I don't think you have to ever mess with this directly, because Pintos has little helper functions to do these kinds of things. Okay, so I have to switch virtual memory from one page table to another page table. Thankfully, the kernel is mapped at the same location in both page tables, so it won't map itself out of existence, which would be another fun gotcha if you had to write that part yourself. If I change out the page table, what else do I have to do? Is the page table the only place that page table entries are stored? I'm getting grumpy because you all should know the answer. We talked about this in CS24. Man. Oh, man. Translation. Look aside buffers. Yeah, right? So that's the other place where page table entries are stored. If I change the page table, are those entries valid anymore? Not really. So I need to flush the translation look aside buffer cache. which means I'm going to have slow memory accesses for a little bit while it gets reloaded. So that's another thing that has to happen here. Okay, so you can see that all of this slows things down. We would like to avoid context switches if at all possible. That's why a rough estimate of the impact of a context switch is about 20,000 instructions. That's the kernel tasks part. That's the part of saving the PCB state, restoring PCB state, flushing the translation look-aside buffers, and off you go. So it's not free. It definitely costs a little bit of time and energy and effort. Okay, so we want to minimize the amount of time this takes. And when I say 20,000 instructions, I should probably also say that's on IA32, x86, 64, because it turns out that there's processors with hundreds and hundreds of registers. And they'll actually group them into register files. And if you want to switch processes, all you really do is switch from one register file to another one. That's a lot faster. You know, so it just depends on the technology that you're using. Sometimes context switches can go a lot faster. But still, they're going to take some time. They're not free. And while you're doing them, you're losing time to do other things. Okay, so that's important. We also have these queues, and we're going to start talking about how we actually manage processes that are blocked. Typically, we will have some kind of queue, and you'll notice that it's a very different approach. I want to actually spend some time in a future lecture talking about how to think like a systems programmer. Because there's a whole bunch of stuff you do in user space that if you tried to do in a kernel, you'd have the worst operating system implementation ever. And so I'd like to spend a little bit of time talking about that at some point in the future. But you get a hint of it here, and you'll get a hint of it when you get into Pintos, where you have one data structure, and instead of having linked lists where elements point to that process control block, the process control block itself holds the pointers to previous and next elements in the queue. And you can actually run multiple linked lists through a single data structure. And so it's a very clever optimization of memory management and so forth, so that you don't have too much to actually manage as far as dynamically allocated memory. So we have queues. Elements hold pointers to the relevant process control blocks. You can think of it that way conceptually. And so you have a run queue or a ready queue that holds all the processes that could run would they have a CPU. It may be that we do things way more complicated than just having a simple linked list. Remember multi-level feedback queues? Well, we might have 16 queues instead of just one. Okay, and somewhere you have an array that points to the first element of each of these queues. You have something like that. Linux happens to manage like a binary tree for some of its schedulers. I can't remember if that was the completely fair scheduler or the O1 scheduler. We'll talk about those when we get to them. But basically, it keeps all the processes in a tree in sorted order by priority, and like the bottom left one is always the one that gets to execute next. Okay, so it can be much more sophisticated than just a queue. But we still call it a ready queue because we're simple like that. Now, since processes do block on long-running operations, you see we can block on peripheral read, things like that, read data from a network socket, wait for another process to terminate. You call wait PID, things like that. You call sleep, which is really nice. You have various things like that. You need to get them out of the ready queue and store them somewhere until they can proceed again. And typically, it's an interrupt handler that says that process can now progress. Now, interrupt handlers have real serious constraints on them. You guys may have run into a few of those kinds of details on your second project, but you're going to run into a whole bunch more when you start getting into Pintos. One thing interrupt handlers are never allowed to do, I don't know if anybody knows this offhand, but one thing interrupt handlers are never allowed to do is to block until something can, until they can proceed. Interrupt handlers are not allowed to do that because guess what? They interrupt everything. They hold the CPU. They're not allowed to block. They have to run to completion. And so like I say, it has to be short, simple, and fast to keep from holding anything else up. So to solve this problem, to make it easier, OSs don't just keep one collection of block processes, because if they did, then the interrupt handler would have to be like, oh, I'm a timer interrupt. Let me run through all the block processes and see which ones are waiting on a timer. Okay, these are, and this subset is now able to proceed. So I'll go ahead and move that subset into the ready queue. Why mess with that? Why hunt through a whole bunch of processes that it doesn't care about? So what the OS will typically do is maintain a queue for each device the thing can block on. And that way, when the interrupt handler goes off, it knows exactly which queue to look at. Okay? Now, there's many other things that you can do in here as well. I'll just give you like a big, ginormous hint for the third project. One of the things you have to do is implement passive sleeping. I don't care if you do polling or spinning on something in Project 2, but you're not allowed to do it in Project 3. Project 3 is where you have to start becoming sophisticated. And so what you can do is maintain a queue of processes that are waiting on the timer. And there's various ways that you can do it, but one easy thing to do is to always store them in order that they need to wake up. So that the ones that need to wake up soonest are at the front, and the ones that need to wake up furthest in the future are at the back. That way the interrupt handler will always run as short as possible, because it can just go down that queue until it's too far in the future, and then it can stop looking down the queue. So there's things like that you can always do to make your interrupt handlers a little bit faster. And that'll improve overall system responsiveness. Okay? Things like waiting for a signal. Well, you can create queues for various signals. You can create queues for processes. I mean, there's a lot of different ways you could structure this. One thing you have to do is think about, well, how many processes generally are actually going to be waiting in this context? So you have to think about how you actually want to structure these kinds of things. Thankfully, this is not something you have to care about very much for Pintos. But if you're designing a real operating system with things like child process termination, that you need to reap the child and so forth, then you have to think about these kinds of design questions. Do I want to have a queue per process? Do I want to have something where I can chain processes to another process when they wait so that I can inform them right away? You have to answer those kinds of questions. Are there any questions so far? All right, you can probably see exactly where this is going. This is not terribly complicated yet. So this is an example of how we might structure our system. Okay, we have our ready queue, which again may not be a queue, but it's definitely processes that are ready. So they're waiting to receive the CPU. The line going to the right of the ready queue is obviously governed by some scheduling mechanism. We'll talk about where scheduling fits into this picture in a second. But new processes come into the ready queue. Processes that are booted off the CPU go back into the ready queue. And processes that become unblocked go into the ready queue. Okay? If it terminates, it goes off the CPU into nowhere. So it goes ahead and terminates. If it decides to perform some long-running task, then based on the device that it has to wait on, or based on the circumstance, it goes into a corresponding wait queue to say, this is now what I need to wait on. So you access the first physical storage device. Well, that thing can generate interrupts. And so the dev HDA queue would be traversed by the dev HDA interrupt handler that goes ahead and figures out which processes can then proceed after a read or a write completes. And then it can go ahead and move back into the ready queue. Okay? So again, this is one of those things, when you look at Pintos and when you look at real operating system implementations, you'll often see that these task structs or thread structs will have one queue pointer, or one set of queue pointers that basically correspond to which queue the thing is currently living in. And so you can see how a process would move from queue to queue as it does various things. So you really only need one. You don't need one for each. That takes up too much space. Okay, any questions? Alrighty, so what's really neat about this is you'll get to build like very simple little versions of this in Pintos. So it's not like you have to implement the whole kit and caboodle yet. You can just start out with very basic stuff. Like you'll build a timer queue, and then your scheduler will start getting a little bit more sophisticated on the ready queue side of things. So you'll see how it all fits together as you get into Project 3. Okay, yeah, it is a large and complex topic. It's really cool. I can't wait to talk about it because there's stuff in there that blew my mind when I saw it, and it'll probably blow your mind as well. So I'm kind of really excited to get into that topic, but not right now. We'll talk about it in probably a week or so. Scheduling can definitely be applied at different levels, and this is another thing you may not be familiar with. But when we think about scheduling, we typically think of who gets a CPU next, but there's various other places that we can apply scheduling as well, and that historically were applied very heavily. So you have long-term scheduling or job scheduling, which is basically who gets to start running. So this is, I'm queued up on the tape, waiting to run. When do I actually get to become a new process that starts to execute? You may have heard this term spooling before. Typically you hear it in the context of printing. But in these batch execution systems, it was the job is ready to execute. We need to go ahead and load it into the system to execute. And spool actually is an acronym, which I'm not even going to bother to try to remember. You probably shouldn't either. But if you're curious where that term came from, that's where it came from. So basically, the long-term scheduler has to pick who gets to start running. And if you think about it, we don't have anything like this on our current computers, which is fine. We don't really use them that way. But if you had 20 jobs and you can only run 5 at a time, which 5 do you choose? What might be good things to think about when you're trying to figure out which 5 of 20 jobs should actually execute? Anybody have any guesses? How long the job is going to take. If we know that, that's a great thing to know, how long the job is going to take. Any other ideas? Yeah. Oh, you just putting your hand up. So, yeah, do you have an idea?
So if like we have one job that does a lot of I/O, I would want to start that job first.
Okay, so that's an interesting one. If you have a job that does a lot of I/O, then you might want to start it before some job that does a lot of CPU. That's another interesting one. If you know that, which is always interesting because part of this is like guessing how jobs are going to behave. Let me go ahead and start spelling this out because we don't have a lot of time. Basically, the goal of the long-term scheduler is to try to maximize the utilization of all of the hardware in the batch processing system. You guys are starting to think about these things as you talk about this. What if all the processes are I/O bound? What if we only had I/O bound processes to run? How much would our CPU get utilized? Yeah, like hardly. Oh, it would make me sad. Basically, it'd be handling interrupts all the time. That's all it would be doing. And then we go back to waiting on stupid tapes. Okay, so that's bad. We wouldn't get to use our CPU much. What if all the processes were CPU bound? Well, there's a couple answers to this one.
Either some processes don't get to run fast enough, or some processes just take forever.
Basically, yeah, they're all competing for this one shared resource. Context switches become the bane of our existence because anytime we spend context switching, we're not using executing programs. So we basically would get into a situation where it's like, well, just let one go and let it finish, and then let another go and let it finish. But the thing is that we're definitely not utilizing our peripherals. So we have a couple of issues that we can run into with CPU-bound processes. So what the long-term scheduler tries to do is get a good mix of I/O-bound processes and CPU-bound processes. Because while the I/O-bound processes are waiting for I/O, that processor can be used to do CPU-bound process stuff. And then when I/O becomes available, then the operating system can kick off the CPU-bound process, let the I/O-bound process do its thing a little bit, and then keep the I/O peripherals utilized. So basically, the long-term scheduler is trying to maximize the overall utilization of all aspects of the hardware. You can probably imagine why this was important for batch processing systems because I'm paying a lot of money for this big, giant, room-sized CPU and my printer, and I don't have a monitor. I just print everything because I suck, and that kind of stuff. Okay, so long-term schedulers would run on the order of every few minutes. I think you can get to that. So anyway, a process terminates. I need to figure out who comes into the system next. That's when the long-term scheduler would make some decisions. Okay, now we typically don't have a long-term scheduler, or should I say it this way? The user is the long-term scheduler, because if the OS becomes unresponsive, or I get grumpy because my disk is churning all the time and I'm not actually able to get things done, then I'll just kill things myself. So I'm the long-term scheduler. You're the long-term scheduler on your system. So we really don't have that anymore. We basically only have short-term schedulers, which govern only the CPU. Okay, so that's the short-term scheduler. There's another one which is interesting, which let's say that the long-term scheduler makes bad choices. Well, in that case, the medium-term scheduler can actually suspend and resume processes on its own. So if you're wondering why we have suspended processes, like on Unix, it's not just so that people can hit Control-Z and then go do something else. It's nice, but that's not a good enough reason to take the time to implement all that stuff. It's because medium-term schedulers needed a mechanism to actually be able to tune the process mix when they actually, the long-term scheduler made bad choices. If you suspend a process and it's not receiving the CPU anymore, what can we do with its memory? Page it all out to disk. So now we've freed up all that physical memory for other processes to use. So you can imagine that a medium-term scheduler has a lot of power to free up resources when you have too many processes using the wrong kinds of resources for everybody to get along well. So that was the purpose of medium-term schedulers. Again, we really don't have medium-term schedulers. I think maybe, okay, so I graduated in 1998, and so UGCS was still a thing in 94. We could all sit and work and stuff. And I think over that 94 to, so 22 years now, I've probably suspended processes so that other things can run maybe 3 or 4 times. So you can imagine, okay, medium-term schedulers, probably a great idea when they were needed, but they're not really a thing anymore. Okay, but this is where these schedulers slot into this picture. And you can see that I've really simplified things, okay, because the block suspended queue and the block queue are going to be much more sophisticated than we actually have in the picture. And the ready queue we know is going to be more sophisticated than we have in the picture. But this is where the schedulers govern things. So the long-term scheduler governs entry of processes into the ready queue, so when they start. The short-term scheduler governs who gets to move from ready into the CPU. And the medium-term scheduler governs who goes from ready back to ready or simply back to a suspended queue instead. Okay, so the medium-term scheduler gets to govern those kinds of things. Any questions? This is your 1,000-foot view of process management and process scheduling. So if you have any questions now, it's good. If not, then what we'll do next time, so I think this is the last slide, is start talking about how we build threads into all of this and how we implement this on the system. So we'll start talking about that next time.